Welcome to the LemnaTec Academy. In this video, we will finally connect almost all strings to create an analysis definition, which then can be used to analyze your data. So let's have a look at LemnaExperiment again. Let's look at the analysis section of LemnaExperiment and open the analysis definition page. We see a list of existing analysis definitions here. If you open this for the first time, this list would be empty. Right now, I want to create an analysis definition from scratch, so I press the Add New Analysis button. Here, we see a lot of things that we can and need to adjust. If you create your analysis definition for the first time, most of these parameters are still disabled. You need to start by importing analysis code. More on this in a second. But let's start here now at the top. Here we can enter a name for our analysis and press Rename. However, this won't change anything in the database yet, because the error message below. We still need to define what shall enter the analysis and what shall be the result we want to use. But let's continue step by step. The recording configuration selection is not really required. It's more convenience by which you can restrict some of the selections below. This may become helpful if you have a lot of different camera labels or created a lot of vessel configurations in LemnaExperiment. For now, we are fine with the catch-all selection named All. The first important selection to be made is the executor. This defines which program shall actually execute the analysis. Currently, we support LemnaGrid and Lemna3D, but more might be added in the future. Until now, we developed all analysis using LemnaGrid, so we are fine with the default. Now it gets really important. We have to select which code, aka which analysis, LemnaGrid shall be executing. There's a drop-down list with a few analyses we have added before. But I like to use the multi-plant analysis we created in earlier videos. In order to do so, we need to import it using the Import button and select the file. Oops, it looks like we made some error in our grid. Let's go back to LemnaGrid. In this analysis, we used a single image, so a single reader. But we may use more than one. For instance, if you have a turner in your system, we may want to analyze the plant from different angles in one analysis. Therefore, we need to identify the different reader devices by some means. The solution is to provide a short caption to them. Let's say we call this reader RGB top. For reasons which will become clear in a moment, we need to name the vessel configuration maker device as well. Let's call it VC RGB top. Now we save the modified grid and try again. We are back in LemnaExperiment. Now we can import our modified analysis. This time it worked. You see the code name has changed to example3 version 1, and in the input section we have a line which starts with the name of our reader device. But first, one more remark on the code. If you import another grid named example3.iac, it will become example3 version 2. If you import a grid named example3.vo4.iac or example3.v4.iac, it will become example3 version 4. It is a good idea to keep the grid together with the snapshots you have used to develop the analysis at some place in your file system. That said, if you accidentally deleted the grid, you can export any grid using the disk symbol. This creates a copy of the grid on your disk. Any changes to this exported grid will not affect the grid used by LemnaExperiment. Let's look at the input section. We have one row for each reader device found in the grid. The grid we've imported was a grid to analyze images with multiple plants in it. Therefore, we are in multi-plant mode. This is also indicated by the green message at the top. Multi-plant mode is identified by the existence of a vessel configuration maker device, or its equivalent in other software such as Lemna 3D, which has a name. If there isn't a vessel configuration maker device with a name, we are in single plant mode. I will show an example in a second. If we have multiple reader devices in our analysis, their images may have different sizes and perspectives. Therefore, each may need its own vessel configuration maker device. Or some may share one if they have the same size and perspective. Therefore, we need to assign which vessel configuration maker device defines the sample position for each reader. With just one reader and one vessel configuration maker device, the selection is easy. Now we have to tell the system which image from which camera shall be used for which reader. This has three elements: the name of the camera itself. This is a bare name without any subtypes. The subtype to be used. Subtypes are only a thing with certain more complex cameras, in particular with PAM. These cameras take more than one image in a single recording, and each image is made under different conditions. So you need to pick which image to use. If you're familiar with PAM measurements, let me give you a simple example. The grid shall calculate the FV over FM value. The PAM takes two images called F0 and FM. So we will have two readers, one for F0 and the other for FM. Therefore, we have to define which image goes into which reader. The third element is a camera label, by which you can distinguish between different sensor unit configurations. These may differ, for instance, in exposure. The names you see here are those you have defined in Lemna control. Finally, we have to choose which vessel configuration to use. If you want to use the configuration you created in Lemna Grid itself, then choose Add Intrinsic exclamation mark. Alternatively, you can use one of the vessel configurations you created in LemnaExperiment, which match the camera name and the selected recording configurations. More on the vessel configuration editor of LemnaExperiment in the next video. But now let's import our single plant example. As previously, the name of the code became selected automatically. In the input section, two columns related to the vessel configuration are now disabled. And the remark at the top states that we are in single plant mode. As shown in the previous video, we need to define not only the inputs, but also the outputs for our analysis. More specifically, which parts of the output shall be written to the database. Lemna Grid creates a lot of data to start with. Each writer can create 20 or more different result parameters. And we may have multiple writers as well. But we rarely need all those data. For instance, in our color analysis example, we are mostly interested in the average color of our objects rather than the principal second moment of the large axis of our objects. And the name of the result parameters are more technical than they convey a biological meaning. Therefore, we can select and rename result parameters in the output translation section. On the left of this table, you find the name of the parameters as given by Lemna Grid. The first part, plants in this case, is the name you gave the respective writer. Everything after this is the name of the parameter as defined by the writer device itself. You have now two options to select a parameter. Press the arrow button. This copies the name from the left to the right. You can change this name after you double-click in the field. The second option is to double-click an empty field and enter a name directly. You may have noticed the red error message is gone now. Please note certain parameters, such as mean color red, have only meaningful values if you add the appropriate properties device to your grid. In this case, the mean color property device. If you send a grayscale image to a mean color property device, it still will report mean color red, mean color green, and mean color blue, but they will all have the same value. In the grids we discussed so far, we had one object per image or per sample position. However, this may not always be the case. For instance, you might be interested in the size and number of leaves at each plant. In the original case, we had one row of data per sample in our result table. But now we may have multiple objects per sample, each with its own row of result data. And even worse, we may have multiple writers, each of them may have different amounts of objects. Another problem might be that in rare cases, LemnaGrid produces more than one object per sample, even though it shouldn't. In order to handle these errors and the multiple object scenarios, we need to define how to deal with multiple data rows for one sample. This is done using the collection mode. We have 6 different modes. The first 4 address the issues with LemnaGrid when creating multiple objects instead of the requested one. Accumulative takes the sum of the values of a parameter provided in the data rows for each sample. This works good for area-like values. It is also the default. Average takes the average of these values. And minimum and maximum do what they say. The other 2 are a bit more complicated. Expanding. This handles the case that we have multiple objects per sample. Consider you have 2 writers, one reporting data on leaves, the other on buds. For simplicity, assume we are interested in the area of each object only. Consider further, we have a sample which has 7 leaves and 4 buds. Then the result table for this sample will look as follows. We have 11 rows in our database. 7 rows will contain the area of the different leaves, but the values for the buds area is set to NaN. NaA or none stands for not a number and marks missing data. The other 4 rows will have NaN, none, in the leaf area and the true values for the 4 buds in the buds column. The same is done for whatever number of leaves or buds the other samples may have. Individual. This was added in LemnaExperiment 24.11. It combines the 5 other modes on a per parameter base. You can define any of the 5 other modes for each result parameter individually in the output translation section. Let's consider a grid with 3 writers in the same example as before. We have one writer reporting data on leaves, the second on buds, and a third reporting data on the whole plant. And we like to get the leaves area and the bud area and the plant height. For the leaf area and the bud area, we select expanding, and for the height, one of the 4 other, let's say maximum. So we get one number for each sample for the plant height, but 7 values for the leaf area and 4 for the buds in our example. The leaf and bud area parameters are treated as in the expanding case, which gives us 11 rows with 2 data columns. Then we add one more column for the plant height and fill it in any row with the same single plant height value. In the next section, we can add formulas. These can be used to derive additional parameters using the results from other parameters as input. You can use this, for instance, to calculate the height of the plant relative to its width. First, we need to give the new result parameter a name. Let's say relative height. Then we can add the formula. Select plant height, divide by width times 100. You can use the cursor keys to navigate through the formula, and you can use the backspace to remove elements. If you are done, press Add Formula. This formula will now be executed by the analysis executor after LemnaGrid has done the actual image analysis. The result became part of the results table in the database. The final element is a bit more technical. The analysis executor can execute more than one analysis in parallel. However, depending on the analysis itself, your computer may or may not have enough resources to run 2, 4, 8, or even more analyses in parallel. If there's no machine learning involved in the analysis, the default values are usually good for a first guess. The worst what could happen is that the analysis runs slower than they should. However, if you're using machine learning, then you need to manage the GPU resources. Make a test run in LemnaGrid and monitor the GPU RAM used during the machine learning part. You can monitor this, for instance, in the task manager. In the machine learning part, the GPU RAM will go up. As the recording of this video, only GPUs from NVIDIA are supported. So you shall look for the GPU in the task manager. If the GPU RAM is used almost completely, then set the number of required GPUs to 1. If the GPU RAM is used less than that, then take this value, round it up generously, and enter the required GPU RAM. In this case, 2 machine learning jobs may run in parallel on the same GPU, provided the sum of the required GPU RAM is less than the available GPU RAM. As with other dialogues, the values here are automatically saved, so you just can leave this page. But let me make a few remarks on version and copies of analysis definitions. I told you that you may import modified versions of an analysis grid or an IAC file, and that this will become a new version of the same analysis code. Likewise, you can create a new version of an existing analysis definition using the New Versions button. If you want to update the grid to a new version as described earlier, you need also to create a new version of the analysis definition to take advantage of. Analysis definitions that already have been used to create results in the database cannot be changed anymore and cannot be deleted. You only can create a new version of it and make changes there. But if you want to create a similar analysis for a different application scenario, I recommend to create a copy of the analysis definition and rename it and make your changes there. So that's it. In this video, you learned how to create an analysis definition and all its options and features. In the next video, we will have a look at the vessel configuration editor of LemnaExperiment. See you there.